Right. So let's get started with Lab 11, which is multi-threaded processor, network processor. So in this, we have to design a five-stage pipeline, which has four threads, right? So that's four-threaded processor that we are supposed to design. For that, we have started with our the single thread simple pipeline, five-stage pipeline that we designed and built. We built upon that. We made a very simple, very minimal changes onto that to achieve the four-threaded processor, right? So let's see what those changes are. First, we have four threads, four different threads. So corresponding to that, we have four different program counters. So PC0 corresponds to the first thread, PC1 corresponds to the second, and so on. So we have four different program counters. And for the fourth thread execution, the kind of the kind of execution we are looking at is coarse-grained multi-threading, simultaneous multi-threading, right? That means the four threads are interleaved. So first, at the first cycle, you want the instruction of thread 0. In the second cycle, you want thread 1. In the third cycle, you want thread 3. In the fourth cycle, you want thread 4, like that. And this actually eliminates the need for any hazer detection unit for putting bubbles in case of dependencies or any forwarding units. This is because since it's a five-stage pipeline, these instructions are automatically they're structurally apart. So by the time the first instruction of thread 0 that has done writing to the register file, only then will the second instruction of thread 0 start fetching the register file. So in that sense, you won't have any dependencies. That eliminates the need for any HDUs and forwarding units and stuff, right? So the way I've achieved that interleaving is through enables. So in the I instruction fetch stage itself, so what I've done is I've written a simple counter logic that I'm assigning. So TS is nothing but a count. So at every clock cycle, it's going to keep on incrementing. And so it starts with 0, 1, 2, 3, and then it goes back to 0, 1, 2, 3, like that. It's a saturating counter, 2-bit counter, right? And corresponding to the value of the thread select, I've assigned enables for that. So I've defined 4 enables corresponding to each of the 4 threads, and I will only increment that particular thread if the count is equal to that particular thread's number. If the count is 0, then enable 0 will be made high, and that particular program counter is allowed to latch onto that particular address, be it PC plus 4 or PC plus 1 or branch target address, right? So that is that particular hardware is synthesized here. So this creates a mux. Either if the reset is if the reset is asserted, then we either write 0 to the program counter, or we keep on incrementing every cycle unless the branch taken is false, or if the branch taken is true, we'll latch it with branch target address. Now all of that, the select line for that mux is going to be enable and enable 0. So this enable is the global enable, right? So that is the enable of the entire processor, and this enable 0 has to do with the thread select. So similar logic I have written for all the 4 program counters, and this is going to result in execution like this. So the TS here you are seeing, that is the thread select. So as you can see, after the enable is asserted here, it goes from, at every clock cycle it keeps switching, right? Just a second. So enable 0, enable 1, and then enable 2, enable 3, and then back to 0 again. 0, 1, 2, 3, like that. And if you look at the program counter, what I've done is for the thread 0, I've initialized it with 0. For the thread 1, I've initialized it with 128. Thread 2, it's 256, and thread 4, it is 384. Right. So the reason I've done that, I'll be explaining little later. So let's see if that's actually happening, right? So as you can see, after the enable is asserted, first you'll get PC out as 0. That is the very first instruction of thread 0. After that, you get the very first instruction of thread 1, very first instruction of thread 2, very first instruction of thread 4, and after that back again, second instruction of thread 0, second instruction of thread 1, second instruction of thread 2, second instruction of thread 3, so on, right? So that keeps happening. So the reason I have done that is, when we come to the instruction fetch stage, right? So I'm using same instruction cache, right? So there again, it's a design choice that I've made. Either I could have instantiated 4 different instruction caches corresponding to the 4 different threads, and then go ahead with that. That would also work. But what I've done is I've used a single instruction cache, and then I've given 4 different regions for each thread, right? So for thread 0, I've given the region between 0 to 127. That's 128 instructions, right? And for the thread 1, I've given the region between 128 to 255. Again 128 instruction. For thread 2, it starts from 256 to 383, 128 instructions again. For the the last thread, I've given from 384 to 511. That's 128 instructions. So in instruction cache, you have 4 different memories corresponding to 4 different threads, right? So all of the instruction, so we have a single PC out, right, that fetches the thing. So the PC out will be varying between threads, right? So that is the idea. So I'm fetching the same I'm using the single instruction cache to fetch the instructions. But when it comes to instruction decode, I've used 4 different registers corresponding to the 4 different threads, but the decoding unit and the immediate generator unit, that is the same. That's because all the 4 threads use the same RV64 ISA. So the opcodes and all are not going to vary, and the function fields and all, they're not going to vary. So one decoding unit is sufficient. Same thing with immediate value generator, right? But the register files they should be fetching from should be different. Again, that's a design choice. If I wanted, I could use a single register file, that's 32 register files, and then I can divide it up. For example, register 0 to register 7, I'll give it to thread 0. Register 8 to 15, I could give it to thread 2, and so on, right? But I made a choice to not do that because when we implement bigger processing things, so we might need more registers to store intermediate values. So that proves inexpensive compared to the data memory fetching, right? So if we are storing the intermediate variables in stack or something, that'll prove very costly. So I made the choice of using 4 different register files itself. Hence the the register 0, register 1, 2, and 3 there, and I've given the corresponding signals for that. So for example, if you can see, it's I have the appropriate designations here corresponding to that thread. And then so that is about the instruction fetch stage and instruction decode stage. From there, after the those register files are fetched, so I am assigning all of them. This is something like a thread select stage, right? So all the intermediate values that I'm fetched, I'll use the thread select IDEX underscore TS thread select IFID thread select value to select which of the register reads should be assigned to the actual should be sent to the next stage, right? So hence this logic. So this kind of synthesizes some mux which acts like a thread select stage, right? And then that's sent out to the EX stage. The EX stage is common, there's nothing new here. So you have the same ALU with the corresponding flags and stuff. And then the branch unit is in the memory stage. Even this is the same. And the data cache that you have here. So all of these are common. And then in the write back stage, there is a difference, right? So in the write back stage, whatever the write back result we are writing, so that write back result, that should be so it doesn't matter if I'm giving the write back result to all of the 4 register files. Only thing I should only write it to the corresponding thread, right, to which I intend to write. So depending on the mem write back underscore thread select, that is the corresponding thread which we want to write to. Based on that, we select only that register write corresponding to that. All others will be set to 0. In this sense, we are making sure that we are writing to the register file of that corresponding thread we want to write to, not the register file of some other thread, right? So that logic is synthesized here. So that is pretty much it. And the 4 threads, to behavioral test it, let's actually we wrote a bubble sort. So very simple code again, right? So we use all the four threads are running bubble sort. So let's look at the initialization file for that. So the data memory is the data memory, what we are trying to do is we are putting these numbers 5 4 3 1 2, right? So at locations in the data actual locations being 0 4 8 12 and 16 and so on. So this is for thread 0, right? Whereas for the thread 1 we are writing from 20 24 28 32 and so on, right? Same thing applies for thread 3 and thread 4. We are doing that, and we want to sort them simultaneously, right? So we have written the machine, I mean we wrote the assembly code, converted that into machine code, and then dumped it here. So these are the COE files for the instruction memory, and this is the COE files for the data memory, right? So now let's look at the behavioral simulation of that. We wrote a simple test bench to query the addresses. We have given mem address query and mem address data here to query the memory, right? So these are the two interfaces. So all we are doing in this test bench is first we are instantiating the things, and then we are changing the address query, right? So we are looking at the memory locations at the starting, and after some amount of time, where after enable is high, right? So then the process would have run and we would be done sorting, so we should get the correct value. So that is a simulation. All right, so okay, so this is the mem address query and mem data out, right? So if you look at this, so at location 0 we have 5, at location 4 we have 4, at location 8 we have 3, at location 12 we have 1, at 16 we have 2. So all these numbers are not sorted, right? So they are in some random order. Same thing, this is for thread 1, that was for thread 0, this is for thread 1. So and then same thing for thread 3 and same thing for thread 4, right? So same thing like that. So after we are done executing, so you can see the results here. Okay, so now the memory location 0 contains 1. You can see the numbers are sorted 1 2 3 4 5. So that's for thread 0, right? For thread 1 it is 1 2 3 4 5 again. So thread 0 and thread 1 are working, right? So again 1 2 3 4 5. Thread 2 is also working, and then same thing for thread 3, 1 2 3 4 5. So that pretty much shows that all the threads are able to execute, and whatever the instructions that are supported, that are actually working without any issues and stuff. So now we'll be dumping that into the NetFPGA and do some processing and test if it works there, if we matched all the timings. So that is usually timing is the only issue that we had faced in our previous labs. Apart from that, we didn't have any issues in actually running single stage pipeline or any of the designs. So we'll check if this has any timing issues, and if it doesn't, it should work on NetFPGA.
Hello guys, welcome to the NetFPGA implementation of the Lab 11 multi-threading pipeline. So here we'll try to load the bit file on the NetFPGA and try to query the memory locations to see the values. So on the four threads, we are running the bubble sort code as explained by my teammate in the simulation part of this video. So basically, we have written the script to query the memory locations, where we'll query the memory locations and check the values for the respective threads before the pipeline is enabled. And the same thing we'll do it after we enable the pipeline. So here we'll enable this pipeline using this reg write, and then we will query the daemon values after the pipeline is enabled. So next we'll move forward and try to load the bit file on the NetFPGA. So our bit file was successfully loaded. So now we'll just try to run the script. So the script ran successfully. So now we'll see the values. So for thread 0, before we enable the pipeline, at the 0th location we have 5, and respectively we have at the 4th location 4, 8th location 3, and 1 and 2. This is it is the same case with all the threads. It is 5, 4, 3, 2, 3, 1, 2. It is 5, 4, 3, 1, 2 for thread 2, and it is 5, 4, 3, 1, 2 for thread 3. Then next we'll enable the values, enable the pipeline. Next, after doing that, we can see that we have successfully run bubble sort on thread 0, as well as thread 1, thread 2, and thread 3. So we can conclude that we have successfully implemented our 4-thread pipeline processor on the net FPGA. Thank you so much, guys.